Hi, my name is Eduardo Rolanca and I will be presenting you our finite project for the finite element method course. So come with me to this journey. So, first of all, we need to understand what we want of this project. So, the objectives are as follows. To optimize a W-shaped 3D printed beam with the 4 circular holes in the web to maximize its load-bearing capacity while keeping the total weight less than or equal to 60 grams. The material used is PLA, and the beam is printed with 100% infill. So now we understand what we want of this project. So let's start from the beginning, the design requirements. So the length must be 220 millimeters, the height must be 30 millimeters, the flange width and thickness must be 20 and 4 millimeters respectively, and the web thickness must be 3 millimeters. The holes has to be 18 millimeters in diameter, center at 45 millimeters along the web, like you can see in the image. The material has to be PLA and with 100% infill, and the maximum weight has to be 60 grams. The geometry of the holes must be remain unchanged, and no material is allowed below the support plane. Finally, we arrive to the fun part, the finite element model. So, for our finite element model, we select the following parameters and the boundary conditions. First, we chose to use the 4-node tetrahedral element due to its simplicity and ease of implementation. While it's true that the 10-node tetrahedral element provides better mesh quality in curved regions, once a certain mesh density is reached, the error becomes negligible. So, in other words, the results convert to an accurate solution. For the boundary conditions, the beam was considered to be simply supported, with its movement restricted in the Y and Z direction. To perform the finite element analysis, we use the OpenSys library along with the tools provided by the Professor Jose Abel and his Gmsh to OpenSys model. For visualization, we use GMSH. We now can go to the original beam, so the no changes has been done. So, if we run the code, we can now see that the original beam has this section or this zone with what we call a high stress element. So, all of these elements that are in red are high stress elements, and the elements in blue are the low stress element. We'll be talking about this later on the video, and that's it for now. So now, if we wanna know the displacement and the stress on the beam, we have to go to here to the original beam again. But we analyze. So we analyze the displacement of the beam. So as you can see here, the displacement of the central part of the beam is the most displaced part. The beam displays 2.31 millimeters along the y-axis.
Hello, I'm Francisco and I'll be showing you the predictions of the optimized model. Using the principal stresses, the von Mises equivalent stress is 1.79 megapascals. By substituting the given data into the equation presented, this gives a predicted maximum load capacity of 3,352 newtons. The predicted maximum displacement under that load is 8.18 millimeters. These values define our baseline for model testing.
So, now we understand the theoretical part, we can now see what the code does. So, come with me. So, as you may see, we have the modified beam before. So, we run the code, and we get this. So, what we are looking at, it's the displacement figure of the beam, and now we can see we have 2.15 millimeters in displacement, besides the 2.2 millimeters in the original beam. So, as you may see, these objects here are supporting the beam. Then finally, we can see the map of the high stress and the low stress elements that had relocated along the beam, and we now can see that the high stress element are located and on the top of the beam. It's logical because there is the point load right above them, and that's it. That is our topological optimization of the beam. So we can say that the FEM method and the FEM analysis works to do a topological optimization of a 3D printed geometry. Thank you for watching.